Okay, now working with limits, we're going to talk about the different types of discontinuities where a graph doesn't continue on. So like polynomial graphs continue infinitely left and right. Uh, that's a continuous graph. Sine graph, cosine graph, those are continuous graphs. But there are four different types of discontinuities. So let's look at this first one, essential. Another name for essential is infinite, and that is when you have a graph that has a vertical asymptote and the graph on either side of that asymptote is headed towards infinity. So maybe this graph, instead of this, maybe look like this, but that would still be an example of infinite or essential discontinuity. And oftentimes they'll want to know the x value, and you would say where x is equal to 0, infinite or essential discontinuity. And you would spell the discontinuity out. I'm okay if you abbreviate after infinite, or you'd say essential. The next type of discontinuity is when it looks like you could actually physically take a step. I don't know if is it an old video game, Donkey Kong? It looked like they were jumping up steps. You've got this graph right here, and there's this big leap between. This is called jump or step. And when you get to college, whichever your professor prefers, use that. And then removable or point. I like to use point because it looks like that. So when you've got a graph that literally just looks like a point's been removed, that's point discontinuity. So we're going to go over the different types. So this first one right here, if you were to graph that in Desmos or in a graphing calculator, notice this is what the graph looks like. There's a hollow dot here, and above that is a point. This would be point or removable discontinuity. Where x is equal to -1. Over here, if you graph this one, I graphed it right there. And notice where x is equal to 2, there is an asymptote. This is the work that you would show for that one, though. The denominator can be factored. So you'd put a negative sign there, and it looks like that's going to be x plus 1, x subtract 2. So notice this factor right there can be canceled. See how that we removed that, we canceled it out. So you would say where x equals the opposite of 1 is -1, that is removable or point discontinuity. And then, so this is now going to be 1 over x subtract 2. So the opposite of -2 is +2. So where x is equal to 2, infinite or essential discontinuity. Just like that. So what that means is where x is equal to -1, if I would have zoomed far out and we would have, in Desmos, there would have been a hollow dot right there. So that's what that graph would end up looking like. All right, so that's what's going on here. So determine if each function is continuous. The function, up here, it told you to find the intervals. So since right here, I apologize for that, since where x is equal to -1 is the only place it's not continuous, then -infinity up to -1, -1, positive infinity. I would like you, even though it doesn't ask you to, I would like you to put the type of discontinuity just so that your brain gets in that habit. All right, and then I'm going to show you. Okay, so for this one right here, notice, remember when we had factored, the x minus 1 canceled? So that's part of when we put the intervals on that one, you have to include that right there. So the intervals would be from -infinity up to -1, and then from -1 up to 2, and then from 2 to positive infinity. That is how you would do those. All right, determine if each function is continuous. If the function is not, find the x-axis location and classify. So again, we'll leave this here. These two have an x in common, leaving x plus 1. So now look at that, x cancels out. So you'd say where x is equal to 0, point discontinuity. I think I'm going to let you abbreviate it there. And then the opposite of 1. So where x is equal to -1, essential or infinite discontinuity. All right, so that's what those mean. Oh, well, that's what's going on there. That's a 1. Okay, let's look at piecewise right here. So again, I would graph both of those in Desmos, but since I didn't, let's do this. So this graph right here, -x squared, that graph looks like this. But this limitation right here says that where x is equal to 2, it doesn't equal that. So down here at -4, there's going to be a hollow dot. Because look at, if we plug -2 in there, or if we plug 2 in there, 2 squared is 4, but the opposite of 4 is -4. And then where x is equal to 2, there's also a solid dot. So this graph is actually continuous. Look at, here's another way to decide that. If we plug 2 into here, the answer is -4. And here, this would be normally a solid line, but in this instance, it's just a solid dot where x is equal to 2. When those agree, it's going to be a continuous graph. All right. So the sine and cosine graphs that look like this, you'll type that into Desmos and you're going to get this, and it's infinitely small. It's just this vibration that you can't really very easily identify the intervals. This would be an example where x is equal to positive pi. These are an example of oscillating. So when you oscillating discontinuity. So when you type that into Desmos and you just see this craziness, it's this reverberation, and it's difficult to pinpoint intervals, that's oscillating discontinuity. So this would be an example of that as well. Oh, and that one, where, so in the denominator, it'd just be where x is equal to 0. It would be oscillating discontinuity. All right, so I think we have a handle on that. Again, type that into Desmos, but because there would be, looks like that's going to be a hole right there. So you're going to have to type that in because this 0 right here, I'll pause this. Okay, as I suspected, when you type this into Desmos, that piecewise, f of x is equal to x cosine 1 over x. So you've got oscillating, but in the middle of that, you also had f of x is equal to 0 when x is equal to 0. So in the middle of that oscillatingness, you also have a solid point. So this would be an example of a continuous function. So you'll definitely need to be relying on your Desmos calculator for this stuff. Okay, so now we're going to come down here and we're going to find the intervals on which each function is continuous. So this is where I was showing you before. If things cancel, there's still going to be a discontinuity point because there's going to be a hole. So for example, this one, that x is not going to cancel. You're going to have x plus 3 times x plus 3 or x plus 3 squared. So only where x is equal to negative 3 are you going to have essential or infinite discontinuity. And so the intervals are going to be negative infinity up to negative 3, negative 3 to positive infinity. So for this one, you're going to have a removable, and you're only going to have a removable because an x factors in the numerator. So in this case, where x is equal to 0, it will be point or removable discontinuity. So negative infinity to 0, 0 to positive infinity. Okay. Again, remember what I said to do here? Besides graphing it, but go ahead and substitute negative 1. So negative 1 squared is 1. So that would be minus 6. So negative 5 plus 8. That height would be negative 3. Put in negative 1 in here. So that would give us 2 subtract 4. That would give us negative 2. These two are not going to agree. This would be an example of jump or step. Discontinuity. But this is the interval. So negative infinity up to negative 1, union. Negative 1 to positive infinity. So that's the key thing here to remember, is that when you're talking about these piecewise and different types of discontinuity, this is what we're looking at. You plug that value into each piece of the function, and if their heights are different on this type, jump discontinuity. So unless this height right here is negative 2, jump discontinuity. And I don't think there's any others that, yep, and then that's just the answer key. All right, this one was a little bit shorter. If there's anything you don't understand, we'll go ahead and meet Thursday. All right, have a great week.